Alrighty, welcome back. Hopefully this question went well for you and for your group. And hopefully you've got 4 people or 3 people in your group and you got 3, 4 people writing. You've got everybody's taking a corner of the whiteboard. Everybody writes, everybody practices. Okay, so here's our question of the day. Astronaut in rest in space, he's holding onto a thruster and it expels gas in the opposite direction. So you're looking for the velocity of the astronaut after firing the thruster. This is definitely an explosion. Okay, so let's consider. Here's our astronaut. He's hanging on to something, right? And your initial momentum, that's my symbol for momentum. Remember, I don't know why it's P, but it just is. And here we've got, gas going that way, and then the astronaut is going to go this way. We're still going to have an overall momentum of 0. All right, I would have drawn a little more there, but I kind of ran out of room. So let us consider how this would work. All right, so we've got the astronaut, we've got the thruster, and we've got a total. If you're going to do this with a chart, right? So we're going to go say before and after. Okay, well, if it's an explosion and he is at rest in space, it is easy to see that he's not doing anything. He's hanging on to the thruster. The thruster's not doing anything. We have a total momentum of 0. Even after our explosion, we know we have to have the same amount because momentum is conserved. So how fast is he going? I don't know, because that's what we're trying to find, right? 84 kilograms. And we want to know the velocity of the astronaut according to the question. All right, so let's just say V. Now the gas, not very much. It's not very heavy. All right, but this is how many kilograms of gas we have. So about 35 grams of gas, but it's going very fast. Right there. Now, just as we did before, this plus this equals the 0. There's your algebra. All right, so 84V plus, now I did this math already so that I would make my life a little bit easier. Okay, multiply those two together. That's going to be equal to 0. Hopefully it's obvious to you that your answer is going to be negative, and your answer is going to be small because, let's face it, that's a teeny tiny number, right? So 84V equals negative 0.03. Whatever that number is. I'll just say it wrong, but I'll do the math right. Okay, so this answer is going to be negative. You can leave it in decimal format. I'm going to put it in scientific notation because it's pretty tiny. All right, now if you left it in decimal form, you'd have 3 zeros, 3, 6, 5. Don't round that too much. It's awfully tiny. Okay, at least keep 3 sig figs on that, even though we don't really worry too hard about sig figs in this class. You don't want to overround a number like that, especially if you're dealing with something like WebAssign. That'll kick your butt. Alrighty, now if this is great, but you said, hey, no, I'm an algebra kind of person. Thanks a lot, Miss Gray, but thank you, no thank you. Let me show you how you do that with just the algebra. Let's give myself a little space to move, and I can go through that part with you. All right, let's pick up the next one here. Okay, so if we were going to do this one in total algebra, what we would say is, alrighty, 0 is my initial momentum. Then I'm going to have, mass of the astronaut, velocity final, plus mass of the gas, velocity final for the gas. All right, so 0 equals 84V plus, what were these teeny tiny numbers again, 0.035. 0.875. Again, it doesn't take much to see that this is going to be pretty tiny. 0.0306. This is going to move to the other side and become negative. What I see a lot of people do is just set these two equal to each other, but then you lose the negative. So don't be lazy. Put the 0 on the other side. All right, we're going to get V equals negative 0.00036 meters per second. All righty, we'll talk again tomorrow about what, where'd my recorder go? All right, so we'll talk again tomorrow about that.